Hello everyone, welcome to YouTube channel Energy-Exergy Theory-Applications. I am Professor Morosuk and I am the author of this YouTube channel. Today we're with the topic exergy. All lectures have a very dynamic style of presentation. Definitely some of you would like to learn more, particularly about exergy. We will be happy to answer your questions and provide with an extended information. Our contact email you can find in the description of each video. Please support our work with a like to this video, subscribe the channel, and share the link with your colleagues. We continue our discussions related to polygeneration systems, and the focus of our lecture today it is polygeneration systems operate below of the environmental temperatures or crossing the environmental temperature. Let us repeat the theory thermodynamic analysis of heat engine that operates at the temperature higher than environment. So all power generation systems, as we already discussed, operate at temperature higher than environmental temperature. So we have a heat engine in direct thermodynamics cycle. Heat is supplied at higher temperature level and heat is rejected to the environmental temperature, and theoretical efficiency it is Carnot, according to the Carnot cycle, T hot minus T0 divided by T hot, or if we have a real system, we can write a W net produced by the system divided by heat supply to the system at high temperature level. And if we discuss exergetic efficiency, then it is exergy of product of the system divided by exergy of the fuel of the system, product W net, and exergy fuel of the system, it is exergy of heat source, so heat at higher temperature level. Now we can discuss another power generation system that operates above temperature of the environment. It is absolute realistic system. It is one of the first application of renewable energy. It is very well known as the system of Darsanval. Darsanval, it is the name of scientists who proposed such a system. So the situation is the following. The heat source is the surface water of ocean, high temperature of surface water, and heat is rejected to the lower temperature of the deep water. So deep water can be 3,000 meters, 2,000 meters. So deep water, and such a system can also generate electricity. That was idea. Definitely efficiency of the system is very low, but nevertheless it is the use of renewable energy. So now let us proceed with exergetic analysis and energetic analysis. From the first law of thermodynamic point of view, theoretical efficiency for the system operate at temperature higher than environment and lower than the environment is absolutely the same. So for this system, we will write T0 minus T cold divided by T0 because it is direct thermodynamic cycle. Absolute the same will be real efficiency, W net divided by T by Q at T0 because surface temperature at surface water is heat supplied to the system. But from exergetic point of view, it is completely different because product of the system is W net produced by the system. This is correct. But the fuel of the system, it is not heat at environmental temperature because heat at environmental temperature has exergy 0. And heat at lower temperature level has higher exergy, because we know the higher temperature if we are below of the environment, the higher exergy, and if we are below of the environment, the lower temperature, the higher exergy. Therefore, for the heat engine that generate a temperature below of the environment entirely, fuel of this system, I mean fuel from exergetic point of view, will be not higher temperature source, will be lower temperature source. So, and I will repeat, exergetic efficiency for such a system will be W net produced by system divided by exergy of cold source. And this we should keep in mind, this equation, because now we will proceed with evaluation similar systems. So the first example, it is regasification of LNG, liquefied natural gas. We know that after liquefied natural gas is delivered in tankers to so-called so harbors, when LNG is delivered, it's called import terminals, and we have LNG storage, and after that natural gas should be regasified to charge to the local pipelines. Regasification process definitely requires energy. And always scientists and also engineers discussed how to reduce energy consumption for regasification process. Now we're discussing only energy analysis and concept. So classical two examples, so use it almost in all terminals overall the world, is the following. Heat for regasification process can be supplied as seawater. So seawater will be transported to regasification process, will, and using this heat from the seawater, LNG will regasify and water returned back to the water source. So for such a regasification process, we need pump, and from energetic point of view, we will discuss specific energy per kilogram of regasified LNG. So there are some values, that average value that for such a system is called open rack vaporizer, and overall the world there is average value of 0.008 kilowatt hour per kilogram of handled LNG. And there is another system which is called submerged combustion vaporizer. Submerged combustion vaporizers can be a little bit larger capacity and with higher effectiveness of the process, I mean time of the process. Idea is the following, that small amount of LNG that is already regasified can be combusted, and heat of combustion process is used for regasification process. So in this way, between 1.5 and 2% of already regasified LNG will be used for regasification. So LNG, so gas will regasify itself, because we will combust some part of LNG that already was delivered to terminal. So this is the only possibility to evaluate regasification processes using specific energy for pump or amount of fuel for that already delivered for regasification, the main part of LNG. So now we will proceed with exergy analysis of these two common concept of regasification, open rack vaporizer and submerged combustion vaporizers. So we always should consider temperature of the environment, because LNG is coming with very low temperature. I would like to remind you that LNG depends on the design of ship. can come with pressure between 1 bar and 5 bar, and if it's coming with the pressure of 1 bar, then temperature will be minus 62 degrees Celsius. So we're below of environmental temperature. So, and we need to regasify LNG to the environmental temperature. So again, I will use my hands. This is environmental temperature, and LNG should be regasified. And we know the lower temperature, the higher exergy. Actually, we will, using any of concepts, always we will destroy the low temperature exergy of LNG. Now, hot sources that will be used. Regardless if we will use water from the reservoir, so from the sea, or we will use the heat of combustion gases. Nevertheless, we need to cool down these sources. So, but now we are above of the environment, and so above of the environment, the higher temperature, the higher exergy. Then we can conclude that regardless will we use open rack vaporizer or submerged combustion vaporizer, from the exergy analysis point of view, it is dissipative systems, because we will destroy the exergy of LNG and we will destroy the exergy of heat sources. And how we can recover exergy of low temperature exergy of LNG. It is very hot topic. It was many years ago and still continue, because market of LNG is growing over all the world. So we will discuss now cogeneration systems. So cogeneration systems based on LNG regasification. The idea is the following. We have storage of LNG somewhere here. We have regasification of LNG, and after regasification, part of the gas we will use for power plant, for gas-fired power plant. So now design of power plant itself is not important for us, because we will discuss only the concept. We can use heat of combustion gases, for example, to regasify LNG. It is like a heat utilization, which is very good idea. But in this way, we should consider that now regasification and power plant, it will be one system that should be discussed. It is cogeneration system for generation electricity and regasification of LNG. Then we are still with energy analysis. Energetic efficiency, it will be W net produced by power plant plus heat of LNG. LNG will be regasified. From energetic point of view, it is positive effect. And fuel, it is mass flow rate of fuel subtracted from the gas pipeline to operate this power plant, multiplied to lower heating value or higher heating value, depends on the school of thermodynamics. And can be another interesting approach. So we can like a transfer of low temperature heat from the regasification process to power plant. How it should be understood from thermodynamic point of view. So if we have heat engine operates between hot temperature source and environmental temperature, as all power plants, we can, using the cold energy, low temperature energy of LNG, plant will operate not at temperature of the environment, heat removed, but at lower temperature than environmental temperature. So we will like decrease lower level of heat rejection from the direct thermodynamic cycle, and definitely work generated within this power plant will be higher, and it will definitely have positive effect to energetic efficiency, because now average level of heat rejected will be not environmental temperature, it will be temperature lower than environment. So this is the idea to implement LNG regasification to the power generation together, and consider this as a cogeneration system. Now we will proceed with exergy analysis. Exergy analysis is very interesting for this, for two approaches. So exergy efficiency, exergy of product, exergy of fuel, and now we need to discuss what is it fuel and product for cogeneration system operates at temperature below of the environment. According to exergy analysis, the product will be only W net generated by system. And the question, why not LNG regasification? Because we need to remember that during the regasification, we will destroy valuable exergy of LNG, because the lower temperature, the higher exergy. And within the regasification process, exergy, so in minus out will be positive. Then it will belong to fuel. Please revise our lectures before. If exergy of material stream is decreased, it belongs to fuel. Therefore, from exergy analysis point of view, effect of LNG regasification, it is not the product, it is the fuel. And exergy of fuel and exergy of air, it is fuel supplied to power plant, and air, of course, we also need for combustion process. So this example demonstrates us that if we're discussing any of energy conversion systems operate below of the environment, we always should remember that the lower temperature, the higher exergy. And if exergy is decreased, it means that it will be not a product, even if it is logically product of the system. From exergetic point of view, it will be associated with fuel of the system. Another example, air separation unit. It is the cryogenic system, cryogenic air separation unit, and operate, definitely all systems operate below temperature of the environment. Air separation system can be very complex, and we can abbreviate our discussion using several blocks. So air is coming, environmental air without pre-handling, coming directly from the environment. After that, we have block of compression. At the end of the process, we have block of purification. So these all blocks always exist, and these actually blocks will operate at temperature higher than environment. And also external product compression also included to purification. So these two blocks in yellow color operate at temperature higher than the environment. Our interest is to discuss three blocks that will operate the temperature below of the environment. It is main heat exchanger, multi-flow heat exchanger, and this is distillation column, entire block, where column itself, it is the part of the entire block. So this is main, so core part of air separation unit. So any of air separation units always produced for chemical products. It is in liquid for liquid oxygen and liquid nitrogen, two very valuable products, and also produced gaseous oxygen and gaseous nitrogen, and sometimes gaseous argon. So many products are produced within cryogenic air separation units. But from energetic point of view, the only one product is considered. Always there is a discussion about liquid oxygen production, and all other products ignore it to discuss the efficiency of this system. So therefore, from energetic point of view, air separation unit always describe it as total power consumption or specific power consumption per kilogram or per kilomole or per norm cubic meter, because it depends on which unit is important. So one more time, per kilogram or per kilomole or per norm cubic meter of liquefied oxygen, liquid oxygen, because liquid oxygen the most expensive product. And as you can see here, there is no discussion about purity of oxygen. Definitely the higher purity, the most expensive product, but it is not included in an energetic characteristic, because oxygen has no energetic energy content, so we cannot put this value for characteristic of the process. We can only put amount of generated product. Now we're with exergy analysis. So what is the benefit to apply exergy analysis for cryogenic air separation unit? First of all, state zero we will fix with air coming from the environment. This is absolutely clear, because air will come to the system, I repeat, with as a real air, and of course humidity also should be included in these discussions. And now we will consider all sources that we need to run this process. For the air compression, to run all compressors, it is multi-stage compression process, we need electricity. For external product compression, this block, we also need electricity. And for distillation column, it's very interesting. Within distillation column, we have compressors and expanders, and some of compressors are linked to expanders. So that's why we have electrical energy supplied and also a little bit generated, but they will compensate each other. Nevertheless, we need to be absolute precise with that. And exergy balance, exergy of fuel, exergy equal exergy of the product of the entire system, exergy destruction within all components within the system, and exergy losses. So exergy of fuel, it is exergy of air coming to the system, and some of electricity that we should supply to the system. So if we will generate a little bit power within the system, within generation column, immediately use it inside of the system, and we will not produce electricity that will come out of the system. Everything will be used through mechanical connection, turbine, and compressor. Now products. Since we are with exergy analysis, we can calculate chemical exergy of all four products: liquid oxygen, liquid nitrogen, gaseous oxygen, gaseous nitrogen, and if also argon will be produced, also argon will be included here. And we should also keep in mind that if we applied exergy analysis, definitely purity of all products also will be included. So here within each of these values, so each of exergetic product of the system will be included not only amount of produced chemical substance, but also purity. And this is very important if further we would like to proceed with economic analysis and economic considerations. Yeah, chemical exergy definitely should be included because air is humid, and all products it's chemical products, but also very strongly recommended, since process is taking place below of the environmental temperature. Physical exergies should be split into thermal and mechanical, and this is really very important to obtain proper results. So it is strongly recommended to divide physical exergy into thermal and mechanical parts. Yes, it will significantly increase complexity of calculations, but if we would like to proceed with proper evaluation of the system, we need to consider all three contributors to exergy stream: thermal, mechanical, and chemical. And now let us discuss about losses of the overall system. So losses of the overall system, it is waste gases that will be emitted to the environment. First of all, air, after treatment, CO2 from air will be removed, and also water. This is the first product. Water is humidity. Means that will be removed from the air, because already for main heat exchanger we need absolute dry air, without definitely without humidity, because temperature is already very low, and also without CO2. And waste, it is also nitrogen stream, which is with other impurities. It is not real nitrogen stream, it is nitrogen with many impurities. This is associated with losses of the overall system. And we can observe that within compression block, within purification block, and even within distillation column, we have multi-stage compression process with interstage cooling in between. We know that interstage cooling, we can handle these heat exchangers as dissipative components, because system is complex enough, and definitely no need to consider all these heat exchangers as productive components, and after that charge to the losses of the overall system. From the beginning, we can say all these interstage coolers are dissipative components and will be charged to the value of exergy destruction of the overall system, and exergy losses will be associated only with chemical substances that will be emitted to the environment. If you found this lecture is interesting and useful, please support us with your likes, with comments for video. Please subscribe the channel and share the link of this video with your colleagues. And our next lecture will be dedicated to the exergy analysis of the energy conversion system by systems with periodic processes. Thank you.